In this video, I'm going to talk about some practical applications of electrochemical cells, notably batteries and fuel cells. So if the overall reaction in an electrochemical cell is thermodynamically allowed, that means that it releases energy, and that means that the cell produces a voltage. And that voltage can be described by the Nernst equation, and so it will be determined in large part by the standard reduction potential, which is simply based on what the reactants and products are. But also, we have that correction factor involving temperature and reaction quotient. It's important for us to remember that voltage is an intrinsic property, so it doesn't matter how big your battery is. A larger battery isn't going to produce a higher voltage than a smaller battery. The only difference between a big battery and a small battery is that the big battery is going to last longer because it's going to take longer for the reactants to run out. If you want to actually increase the voltage of your battery, then what you have to do is you have to take multiple electrochemical cells and connect them together in series. One of the most important properties of any battery is going to be reliability. It needs to produce a constant voltage. If it doesn't, it's not going to run your electronics properly, and it's probably going to break your electronics. And so in order to maintain a constant potential, since the standard potential isn't changing, we need to make sure that we can keep the correction factor term constant as well. So we need to run the battery at a constant temperature, and we need to maintain a constant reaction quotient. There are a couple of basic approaches to doing that. One of them is to have all of your products and reactants be pure solids or pure liquids, so that all of their activities are 1 and the reaction quotient is just always 1. Another approach is to use saturated solutions and have a lot of solid material available to resaturate the solution as any components are consumed. And so essentially then you'll find that a lot of batteries, the insides of them are pretty much a paste or a slurry. There's a lot of solid, a tiny amount of water that allows the current to flow, and that water exists as a constantly saturated solution, maintaining constant concentrations and therefore maintaining a constant reaction quotient. Another important feature of many batteries is the ability to recharge them. In theory, any battery can be recharged. Any electrochemical reaction is reversible by applying an external potential. However, in practice, for some batteries, applying the external potential can result in destruction of the battery. And so this leads to some batteries being more amenable to recharging than others, and that's why you shouldn't try to recharge a battery that's not rechargeable. You're just going to wreck it. So one really good example of a battery that maintains its potential very well is the alkaline battery. In an alkaline battery, we have a zinc anode. Zinc metal is oxidized to zinc hydroxide under basic conditions. And we have a manganese 4 oxide cathode, and at the cathode, the manganese is reduced, again under basic conditions. When we add up those two half reactions, we can see that the electrons will cancel, and we have a stoichiometric coefficient of 2. And the hydroxide ions cancel, so they need to be there for both of the half reactions to work, but they don't appear in the overall reaction equation. And when we look at our overall reaction equation, we can see that every single product and reactant is either a solid, or in the case of the water, a liquid. And so all of the activities are 1, the reaction quotient is 1, and therefore the cell potential is approximately equal to the standard cell potential, and you have a very consistent potential until you just run out of reactants, at which point the reaction stops completely and your battery dies. Another battery that's been very important to society for the last several decades is the lead acid battery. At the anode of the lead acid battery, we have lead being oxidized by sulfuric acid. Remember, sulfuric acid is a strong acid, so it fully dissociates in water to solvated protons and hydrogen sulfate ions. At the cathode, we have reduction of another lead species, this time lead-4 oxide, again in the presence of the sulfuric acid. And when we add up our two half reactions, we get an overall reaction in which lead and lead-4 oxides react in the presence of sulfuric acid to give lead sulfate salts. This particular electrochemical cell has quite a high standard potential, almost 2 volts. Many of your more common electrochemical cells have standard potentials closer to 1 volt, so this is actually quite high for a single electrochemical cell. But in order to run a car battery, we actually need 12 volts, and so to achieve that voltage of 12 volts, we have to actually connect 6 electrochemical cells in series. Now, we do know that there are constant improvements in automotive technology, and we are trying to develop more environmentally friendly vehicles. And so one of the approaches that is being investigated is the development of fuel cells. Whereas in a combustion engine, a lot of the energy released from that combustion reaction is released as heat or wasted as heat. In a fuel cell, we're able to harness much more of the energy released. If we were to be able to use hydrogen as our fuel rather than a carbon-based fuel, we would also then have much more environmentally friendly products. When you combust carbon-based compounds, you wind up generating carbon dioxide. If you combust hydrogen gas, remembering that combustion is simply oxidation of a species by oxygen gas, your only product of your reaction is liquid water. And liquid water is every environmentalist's favorite byproduct of any reaction. In order to balance this out, I need 2 molecules of water and 2 molecules of hydrogen gas. Now, that reaction was pretty easy to balance by inspection, but we wouldn't be able to do any electrochemical calculations on it without knowing the stoichiometric coefficient. And to find the stoichiometric coefficient, we do have to break it down into half reactions. So in any fuel cell, since they all involve combustion reactions, they all involve reduction of oxygen, they all have the same reaction at the cathode. The only difference, of course, is whether your fuel cell is operating under acidic or basic conditions. If it's operating in acid, then you're looking at the reduction of oxygen gas in the presence of acid to make water. And if it's operating in base, then you're looking at the reduction of oxygen gas in the presence of water to make hydroxide ions. If we want to think about the hydrogen fuel cell specifically, the reaction at the anode is going to be an oxidation of hydrogen. And since fuel cells are typically run under basic conditions rather than acidic conditions, we're looking at the reaction of hydrogen gas with hydroxide to produce water and electrons. And of course, if we wanted to combine this with the other half reaction, we would need to have our electrons cancel out. So we would need to double this such that we had 4 electrons instead of 2. And when we add this half reaction and this half reaction, we get the reaction on the previous page, but we have now also determined that the stoichiometric coefficient is 4, which will allow us to do electrochemical calculations to determine how much energy, what potential we can actually extract from this reaction.